on Wi-Fi. One second. Okay. So we left off on Wednesday talking about nucleophiles and electrophiles and sources and sinks, and we're gonna dig into that topic a little bit more today. And we're also going to talk about some other stuff. We're going to talk about the 4 different types of reactions, which are substitution, elimination, rearrangement, and addition, not in any particular order. And then we're also going to talk about bond making and bond making processes. We already talked about heterolytic, heterogenic, and so it's good. There's another bond making process, bond making / bond breaking process that is homogenic and homolytic. So we're going to talk about that. And then we're going to also talk about entropy, which is, delta S, but then enthalpy, delta H, delta G. And in the process of talking about that, we're also going to talk about the activation energy, which is delta G, double dagger, and the rate, K, and then the rated, the equilibrium constant K. All of that stuff is going to be discussed within the scope of looking at certain reactions. And there's a process that we're going to learn to determine delta G, delta H, KEQ, and the rate without actually having the quantitative numbers to do that. If we know the bond strengths, we'll be able to do that. All right, sorry about that. My connection dropped. Let me go back to my screen. Slap somebody at AT&T. All right. What was the last thing? Here. We're also going to learn how to interpret reaction energy diagrams. So let's jump right in and start talking about these types of reactions. And then once we do that, we're going to also look at another set of questions dealing with nucleophiles and electrophiles and sources and sinks. So let's do that real quick. And this handout is, there's 3 handouts on Blackboard. I just combined them so I can put them into my app on my iPad. Come on now. All right. So let's look up top, and we're going to let's look at B first and see what type of reaction happens. So let me put some hydrogens on B. All right. And what do you think happened? Let me put some hydrogens over here. What does it look like happened? Does it look like one of my hydrogens got swapped out? See how this hydrogen here is now replaced by chlorine?
Yeah.
Yeah. So this type of reaction is what we call a substitution.
Which handout are we on?
Say that again.
Oh, which handout is this working on right now?
It's in 2A. Second, I think it's like second module 2A in the assignments folder. All All right, so this is an example of a substitution, and in a substitution, it's basically exactly what it says. You replace an atom or a functional group with a different atom. That's a very watered down definition. But you can see that the hydrogen, one of the hydrogens got swapped out with chlorine. Right, so that's an example of a substitution. All right. Any questions about that? All right, let's look at C. C over here. What do you notice that's different? Let me draw the hydrogens in too. And I'm going to highlight this one. This actually was in that one of the videos that I sent out. Not this exact example, but substitution and addition were both discussed in that video. What type of reaction is this? What do you think? And what does it look like I did?
Addition.
It's an example of addition. You're right. What did I add in this particular case? Right, it looks like I added a hydrogen to this carbon and then a hydrogen to oxygen, doesn't it? Right? Addition only happens on pi systems or on pi bonds. Right, so addition is exactly what it says. It's the addition of an atom or functional group to a pi system. Let me see if I can get that. I'll write the definition up. Oh. So it's the addition of an atom / functional group to a pi system. So pi systems undergo addition. Right? They can't do substitution. All right, so that's an example of an addition. And we're going to look at this in a lot more detail, so don't panic if it's not clicking right away, because we got a bunch of examples that we're going to work through. What about A? What does it look like happening?
Subtraction.
Say again?
Subtraction.
Subtraction, okay. That's not the technical term, but I'll take it because you're right. This is an example of elimination. What do you notice in the product? What did I make? I made a double bond, didn't I? That's one of the key characteristics of elimination is that you always end with a multiple bond, either a double or a triple, right? So this is an example of elimination, and I lost something to form a pi bond. So it's elimination is exactly what it sounds like. It's the loss of an atom or a functional group to form a pi bond. right? And you can see the pi bond that you made right here, right? So you lost the atom or functional group, and you made a pi bond in the product. That's an example of elimination. One example of, so there's substitution, addition, elimination, and then there's a fourth type of reaction, which is called a rearrangement. So I'm going to show you an example of that. All right, so let's see if I can. All right. So the fourth type of reaction is what we call a rearrangement. All right, so a rearrangement is a little bit more complicated, but the basic definition is a migration of electrons, right? It's migration of electrons and atoms. Right, so one of the classic examples of rearrangement is, let me show you what the product is, and then I'll show you what happens. This is my product. Now my plus charge is over here, right? And then the hydrogen that was attached to that carbon is now over here, right? So this particular rearrangement is what we call a hydride shift. It's a type of rearrangement. Right, so the hydrogen and the electrons migrate from the tertiary carbon over to the primary carbon, right? And then by the same token, when the hydrogen and its electrons move over, the tertiary carbon becomes a carbocation. So that's one of the classic, that's a classic example of what we call a rearrangement, where you have electrons and atoms migrating from one atom to another. All right, any questions about the types of reactions? We're gonna do some other examples that are a little bit less generic, and then that way you'll see exactly what we're talking about. All right, so again, there are four types of reactions that we're gonna look at. We're gonna look at elimination, substitution, addition, and rearrangement. Addition and elimination are the reverse of each other, each process. So, and in order to go from, if you get an addition product, in order to go back to your start materials, you'll have to do an elimination. In order to get an elimination product to go back to the start materials, you have to do an addition. So addition and elimination are the reverse of one another. All right, any questions about this? So we have substitution, addition, elimination, and then rearrangement. Those are my four types of reactions. We're okay so far?
So is rearrangement kind of like resonance?
It can be, it depends on the type of rearrangement you're doing. Like if you're doing something like a Claisen rearrangement or something like that, then yes, it's almost like resonance where you only moving electrons, right? But sometimes you're actually moving atoms. Right, so sometimes you're moving atoms, sometimes you're moving only electrons. So it's similar, yes. It's the same concept because the orbitals have to overlap in order for you to share electrons and things like that. So that's a good question. All right. Let's go to some examples, and then we're gonna see if we can apply what we know from here. So let's go down here and let's see what we can do. Perfect. Let's do B. And we're also going to start putting some arrows in, and I'm going to explain like the arrows and all that stuff as we go. So I want to do B, and let's see if we can figure out what's happening in B. All right. So what does it look like happened in B? Going from left to right.
Elimination.
I lost chlorine, didn't I? And then what else did I do? So I lost chlorine. And then I also did something else too.
Yeah, that extra bond on the oxygen.
I made a pi bond. Good. So the way you would show that is by taking an arrow. We've already been exposed to arrows somewhat, but we'll take a curved arrow and put it here. Notice where I stopped it. I stopped it between the carbon and the oxygen. That's telling me that I'm making a pi bond. I know we talked about this before, but you can never get enough of that, right? By the same token, I need to show the chlorine leaving. So I'm going to put that arrow there between carbon and chlorine, right? Does that give me the products that are on the left?
Yes.
Yeah, it does. All right. What type of reaction do you think that is? So notice what I did. I lost an atom or a group of atoms. In this case, I lost a chlorine, and then I made a pi bond. So this is an example of what type of reaction?
Elimination.
An elimination. Good. Very good. That's an example of elimination. I lost an atom or a group of atoms. I made a pi bond. Now the chlorine in this case, when you do elimination, when you do substitution, you always have what's called a leaving group. So the chlorine in this case will be considered my leaving group because it left. All right. Any questions about that? All right, let's do another one. Let's do E. Notice also my arrows. I think we talked about this before, but I'm gonna talk about it again now. So again, if I have a double-sided arrow, a double-headed arrow, that means I'm moving 2 electrons. If I have a single-headed arrow, which I'm gonna show you in a second, that means I'm moving 1 electron. That matters. All right. I'm gonna come back to a couple of examples where we have to use those single-headed arrows. Let's do E. All right. So I have ethyl bromide, and I'm reacting it with OH minus, and then on the other side of the arrow, what happened? What do I have?
Substitution.
Substitution. Very good. Who was that?
Miss Rollins.
All right. Thank you, Ms. Rollins. It's a substitution, right? Let me write that up here. All right. Now, let me add a couple of more layers to this because it is a substitution. You can see that the bromine got swapped out with the hydroxyl group, yes?
Yes.
All right. So let's add another layer, because when you're doing substitution, you have and addition. Substitution and addition both have nucleophiles and electrophiles. So in a substitution, right, your nucleophile, remember I told you you can abbreviate this as NU with 2 dots over it. Your nucleophile is going to attack your electrophile. Somebody tell me what the definition of electrophile. Anybody? If you watch the video, you should know what the definition of an electrophile is.
They like electro.
So yes, a lover of electrons, good. And the way that you find out what site in the electrophile is desirous of electrons is through dipoles, just like we learned several weeks ago. You always look for a dipole, a polarized bond. That's how you know what bond or what atom the nucleophile is going to attack. So in this ethyl bromide, I'm going to see if I can fit this in here. You have CH2, right? And then CH3, right? So you know that there's a dipole here. That's how you know where the nucleophile is going to attack, because the nucleophile is electron rich or poor. Which one? Is a nucleophile electron rich, or look at the OH? It's got 3 long pairs. Is it electron rich or electron poor?
Electron rich.
It's electron rich. All of your nucleophiles are electron rich functional groups. All right. So when this attacks, it's going to attack like this. It's going to hit the carbon in the electrophile that's partially positive. Right? That's what nucleophiles do. Sorry. I live like 10 miles from an Air Force base, and they're always training. All right. So the nucleophile is going to hit that site. It's not going to hit anywhere else in that molecule. Only the site that's connected to the most electronegative atom, which in this case is carbon connected to bromine. That dipole is going to dictate everything. All right. So that's where the nucleophile is going to hit. And then when it does, the bromine leaves with electrons. Right? Notice my arrows. I'm using double-headed arrows, and I'm pointing the arrow where the pair of electrons is going to stop. Are you following? Notice I did not point that arrow. I'm going to use a different color so you don't get confused. I didn't point it here. I didn't point it here. Where my arrow stops, that's where my electrons stop. Right? So you want it, the location and the direction of the arrows matters. And notice I also didn't point it here. Can't do that. Right? If the electrophile is an acceptor, you never put an arrow going away from it, because it doesn't have any electrons to give away. Right? It's always source to sink. The hydroxyl group has the dishes. The CH2 group has the sink, has the open sink to accept the dishes, just like we talked about on Wednesday. All right, any questions about this, about anything so far? So my nucleophile is going to attack my electrophile, and that's how substitution happens, right? Nucleophile attacks the electrophile loses a group. So what would bromine be considered in this case? If it's leaving,
A leaving group.
Leaving group. Bromine is the leaving group. Whenever you do a substitution, right? When your nucleophile comes in, your leaving group has to leave. And there are different types of substitution also, but we're not going to get into that yet. We're going to see that later. All right. So that's a great example of a substitution. And now we're adding in a few more layers to it. We're adding in a few more layers to it. All right, so now we're starting to see some of these terms in action. So you see your nucleophile, your electrophile, you see the leaving group, you see the substitution happening. So let's do another example and see if we can push this a little further. Let's do F. All right. What do you think F? What do you think is happening in F?
Addition.
All right. I heard somebody say it, kinda. Did somebody say elimination? It sounded like Amari. Am I right?
Yeah.
All right. So this is an example. Good. An example of elimination. How do you know that that's an elimination?
Because in the, oh,
Say again.
never mind.
Go ahead.
Because that it ends in a double bond.
Yes. That's how you know elimination happened. Because in the product, you get a double bond. Uh-oh, sorry. You get a double bond. Right? That's the hallmark of elimination, is the formation of a pi bond in your product. All right, let's see how it happened. So we need to make a pi bond, but if you look at this carbon right here, what do you notice on that same carbon over here? What's missing?
The hydrogen.
The hydrogen.
There's a hydrogen missing. So a hydrogen came off. So let's see if we can come up with the arrow. So here, right, we're going to take one of those hydrogens off. And then we're going to use the electrons in the CH bond to make my double bond. Uh-oh, that's too far over. All right, so the OH, comes in, plucks off the proton, and then you lose, and then the CH, the electrons from the CH bond are used to make your pi bond. This process, even though it's not listed as one of our reaction types, we're going to talk about it. What is that called when I pull off a H plus? Anybody remember? Because we've already done acids and bases.
Deprotonation.
Deprotonation, yes. What's another term for it that we used? Or another phrase?
Proton transfer.
Proton transfer.
Very good. Very good. Most of the time when you do if you do elimination with a base, then you're gonna have a proton transfer step somewhere in there. All right. So in this case, this is elimination happening in a acid, similar to an acid-base reaction. You pull off H plus, and then the electrons from the CH bond go back to carbon, but in this case, they're used to make that pi bond, right? You always make a pi bond as a result of elimination. We okay so far? All right, I want to look at a couple of these other reactions. I'm gonna have to, let me see. I don't want to erase that, so I'll just look at, I'll draw it out. Let me do that. Let me add a page here, and then I want to do those top two reactions so we can talk about another, talk about these radicals. Then we're gonna go back and what time is it? Oh, we got plenty of time. All right. So I want to take one of those top examples and give you, show you something related to that. Okay. So there's a reaction up top here. I think it's D. So let's do that one. And then in the product, I think it's this. Yeah. And then BR. All right. Okay. So when we look at that reaction, let me put the hydrogens in so you'll see what happened. And then we're going to talk about how it happened. All right. So when you look at that example, right, what do you notice? What happened? There's a couple of things here that are noteworthy, but what happened going from here to here?
One of the bromines got taken off.
One of
And
the
added.
hydrogens came off, yeah? All right. So what type of reaction is that? If I take hydrogen off and replace it with another atom, what is it?
Substitution.
Substitution. Good. But it's not direct. In this case, this is not a direct substitution like we just saw. This type of substitution happens in what we call a radical fashion. So it's called radical substitution, right? And I'm gonna show you how this happens. And actually, I'm gonna put this BR dot in brackets, right? Because it really is HBr, but I'm gonna show you how it happens. So anytime you have a radical substitution, all of your bond breaking and bond making processes are gonna be homo something. So homolytic or genic. Anybody remember what lytic is? Lytic making or breaking? So we talked about this, it might have been last week.
Breaking.
Breaking, good. And then genic is formation. Right, think about Genesis, the creation. And then lytic, think if you're a biology major, think about lysis, right? Cell lysis, where you lyse or cut cells. Think about that. All right, so homolytic, homogenic. All right, So what the way this happens, normally, it happens in 3 steps. So it happens as initiation. And we're gonna talk more about this, so don't trip. So I take bromine and I shine light on it, right? UV light, and then I break it up into 2 bromine radicals. Right, these are radicals. They have a single unpaired electron. If I could spell single. So anytime you hear the term radical, it's an atom that has a single unpaired electron. Right, a non-metal, because metals like sodium and group 1, they have single unpaired electrons too, but they're not radicals. All right. All right.
Wait, Dr. Russo,
Go ahead.
what is that above the 2 BRs? Is that supposed to be H's?
H nu. Remember,
Okay.
like in G-Chem, the energy
Yeah.
of a photon. All right. We good with that? So that's the formation of bromine radicals. We're gonna talk about this later. I got videos for this and everything, but we're not gonna get to radicals until a little bit later. But while we're here, we might as well talk about it. So that's the initiation step. And then the next step is what we call propagation. So that's where you pull off hydrogen. The term for removing hydrogen is called abstraction. Right, you pull off H dot. Right, so here I'm going to pull it off using one of the bromine radicals that I made at the beginning. Now, the reason I'm doing this is to show you the different arrows, right? So here I'm going to cut this bond homolytically. What that means is that both atoms in that bond, the C and the H, are going to get 1 electron each. All right, so I'm going to cut it like that. Boom, and then boom, right? Notice my arrows. I'm using fishhooks or arrows with a single head. That means I'm moving 1 electron at a time. Right? You move 1 electron at a time. And then my bromine is going to come in and pick up that hydrogen that gets abstracted. Right? It's the reason why it's being abstracted. Right? So you homolytically cut that bond, and then you homogenically make HBr bonds. Let me show you what we get. We're going to get this. There's still a hydrogen here. There's 1 electron on that carbon plus HBr. Any questions about anything so far? All right. So you have an initiation, propagation, and then the last step is termination. Right. And so in termination, you're going to take this radical and pair it up with bromine. That's where the substitution part happens. Right? And the way you do that is to put this electron here and this one here. Again, I'm using half arrows. And this is, what type of bond formation is that? What do you think?
Covalent.
Okay, I did make a covalent bond, you're right. But it's the process to make that covalent bond. Is it homo or heterogenic? Right? Remember, heterogenic, one atom brings both electrons. Homogenic, both atoms bring one electron. So it's homogenic.
Can you repeat homogenic and heterogenic real quick?
I'll write it down. I'll write the definitions down. All right, so this is homogenic. So homogenic, and let me just add a page because I'm gonna run out of space. All right. So we have our bond making and breaking processes. All right, so you have homogenic and homolytic, right? And for homogenic, both atoms supply one electron. Right, kind of like what we see in that termination step up top. That's and genic again is formation. If it's homolytic, then both atoms are going to take one electron. All right, then the other bond making and bond breaking process, hetero, so heterogenic. So one atom supplies both electrons. And again, this is to make a bond, right? Every covalent bond is made up of two electrons. So either each atom is going to have one electron apiece and bring that to the table or leave with it, or one atom is going to bring both electrons or leave with both electrons. So heterogenic is one atom supplying two electrons, and then heterolytic is the opposite, right? One atom leaves with two electrons, right? So those four processes are always going to be at work, right? For homo and homogenic and lytic, this is always going to apply to situations where you use radicals. Right, so that's always going to be involved in what we call a radical mechanism. For heterogenic and heterolytic, this is always going to be what involved for what we call a polar mechanism. Right, so polar and radical, those are the two main mechanisms that we're going to be dealing with in this section. So something can be homogenic or lytic, that's going to be radical. Heterogenic or lytic is going to be polar. All right, so all of that we just went through was for that substitution because it was a radical substitution. It wasn't polar. Right, so it was not direct substitution. All right, any questions about anything? I know this is a lot, but I promise you, once we lay the foundation, everything else becomes trivial. That's why it's always best to get the fundamental stuff down first and then start applying it. All right, anybody still writing this down?
Yes.
Okay, I'll leave it. Any questions about anything? All right, so up to this point, we've looked at 4 different types of reactions: substitution, addition, elimination, and rearrangement. And we've also looked at how to identify nucleophiles and electrophiles. We've also looked at how to use curved arrows to show a mechanism for a reaction. And we've already also looked at the different types of mechanisms, right? Polar and radical. All right. Any questions about anything? All right. So let me go back to here real quick, and I'll put that other page back up in a second. What type of mechanism did B go through that we did?
You said B or E?
B.
E?
Is it polar or is it radical?
Polar.
And how would you know? Say that again.
Is that polar?
Polar. It's polar. The reason you know that is because you're using double-headed arrows, right? Which means that your bond breaking and making processes are going to be heterolytic or heterogenic. Is that right? What about F? Polar or radical?
Polar.
Polar.
It's polar, right? Double-sided arrows. Each atom is either donating 2 electrons or taking 2 electrons, so it's polar. All right, and we know, so D will end up being radical because we just went through that process. What about C? Let's see if we can figure that out, and then we're going to stop. C right here. How would you, well, first of all, what type of reaction is it? And then let's see if we can put the arrows in to show how we got from point A to point B. Is it a substitution, do you think? I'll give you a hint. This used to be a CH4. You see that radical right there? That 1 electron on carbon? That's a clue. That's a hint to the fact that that carbon lost the atom, right? It lost a hydrogen or some other atom. So the end result has to be a substitution. Right? A carbon radical reacting with another radical that's gonna give you a substitution in this case, right? Unless it's some type of addition reaction. All right. How would you put those two together? What arrows would you use if you wanted to show how you made this covalent bond right here?
So for this one, we don't use a double-headed arrow, right?
No, you don't. Very good. Why not? Because can you see
need
that?
to make
Removing one electron,
Yeah,
right?
you got one electron on chlorine and you have one on carbon. So that's telling you that this is going to be some type of homogenic or lytic process. Following? Right?
Yes.
So
Would it be
go ahead.
would it be the arrow going from the chlorine to the electron?
Yeah, we can show that. And then we can show another arrow coming here. No, when you illustrate your homogenic bond formation, the way you do that is to show the arrows meeting. So the arrow
okay.
from one atom is going to meet the arrow from the other atom. What that means is that those two are going to make a covalent bond. Right? And by the same token, if I show in a polar mechanism an arrow starting at one atom and ending at another, that means I'm making a bond between those two atoms. All right, so I just show the arrows meeting up together. Right, and this is homogenic or lytic. We know it's homo because of the one electron. Say again.
Homogenic.
It's homogenic. Right, it's genic because I made a bond in the product. I made a bond between carbon and chlorine. And it's a version or a type of substitution. All right. We're going to do more of this, so don't trip. If it ain't clicking, it's going to eventually. So we're just going to keep moving and keep working. I'm not going to send you the radical videos yet because I don't want to get too deep in the weeds on that. But when we come back to it, you've already been exposed to it, so it should be a little bit easier to follow when we do get to it. All right. I'm going to stop here and stop recording and stop sharing.